So, sir, should we start?
Am I audible?
Yes, sir, you are audible, sir.
Thank you. Thank you very much. Very good morning to all. As we are aware today, we have one another very important topic related with electrical measurements on electronic devices. We have with us Dr. Anuj Kumar, Associate Professor from the Department of Physics of J.C. Bose University of Science and Technology, YMCA, Faridabad. He is graduated from Chaudhry Charan Singh University in 2002 with physics, chemistry, and mathematics, and did his master's in physics from Gurukul Kangri Vishwavidyalaya, Haridwar, and secured first division. He was awarded PhD in microelectronics by Kurukshetra University in 2011. He has worked as project fellow from June 2005 to 6 at Electron Tube Group area in Central Electronics Engineering Research Institute, Rajasthan. He has also worked as research scientist at IIT Delhi from March 11 to June 18. Fellowship by Government of India. His areas of interest are organic and inorganic semiconductor materials and devices, thin films, low cost. So he has guided masters and PhD students during last 15 years, and he has more than 30 international publications in good impact factors to his credit. Thank you very much, sir, for joining us on this Saturday to deliver your knowledge and experience. We have with us our Honorable Shri B.N. Dikshit, sir. Sir, would you like to speak kindly 2 words?
हाँ आशुतोष जी
Sir, thank you very much. Good day, sir. Please, over to you, sir.
ओके सो श्री आशुतोष अग्रवाल जी डायरेक्टर लीगल मेट्रोलॉजी गवर्नमेंट ऑफ इंडिया डॉक्टर अनुज कुमार जी टुडे एक्सपर्ट ऑफ द प्रोग्राम द टॉपिक इज वेरी इंपॉर्टेंट एंड प्लेस डे टू डे रोल इन आवर लाइफ है everywhere you know that there are the voltmeters are there, the frequency meters are there. In laboratory there are the lot of the electrical equipments are there that require the testing. Even the electronic equipments are there that also require the testing of various electrical parameters apart from the electronic parameters, so that require the testing. So now these days the facilities are being available in regional reference standard laboratories. Earlier, the peoples were going to ERTL or ETDC and other places for the testing of those very things, frequency, voltage, EFT, and so many other type of things. The electromagnetic force compensation principle based, whatever the things are there, that very things are also being tested there. Even if it is the battery based things are there the frequency and voltmeters are being different, so those things are being also tested, so today our expert Dr. Anuj Kumar is there. He will explain all the things in very described manners, so all the participants from the regional reference standard laboratories and other places of the legal metrology and the scientific officers and the industry people who are participating in these very programs, they will be benefited much. So I request Astoshi to invite Dr. Anuj Kumar ji to give his lecture. Thank you.
Thank you very much, sir, for your kind and motivating words. Thanks a lot. Thank you very much, sir. Now, I would like to request Dr. Anuj Kumar to kindly enlighten us with your vast knowledge and experience. Over to you, sir, please.
Namaskar, sir. Good morning, all of you. So this is my pleasure that you invite me this opportunity. So thank you, sir. Thank you, Dixit sir, Agarwal sir, for this opportunity. So let's we start about the electrical measurements of solid state electronic devices. Basically, the name of the solid states, the first we start with the resistance, because the resistance is a main fundamental of characteristics of the material. Now, first the beginning, we start with the materials characteristics, and then we go to the next in devices. So the resistance is basically, this is the fundamental characteristics of the material, and this is basically this is indicate about the how the our electrons are flow in a material. So in normally in our classes in 8 and 6 and 8 standard, so we know the resistance is directly proportional with the length or area, and the measurements and the symbol of the resistance is basically we represent the by the mu. And in the next is basically the resistance is basically emphasized by the Ohm's law. So this is all in a scientific world. So this is the well-known rule and the law, the Ohm's law. Basically, the Ohm's law basically, if suppose if we apply the voltage in terminals of any conductor, so this is the current is flow, but in current flowing there is some obstacles, and this obstacles is represented by the resistance. So V is directly proportional with the current, and suppose if we remove the proportionality constant, then one term is arise here is the resistance. So resistance basically, this is what is the resistance basically, and then we can calculate the resistance in terms of the voltage and the current basically. So now the Ohm's law basically, suppose if we apply the voltage in a circuit, so there is the movement of the current, or
Sorry,
you
sir.
can
Hello?
say,
Sir,
hello, sir,
if it
sir,
is
I am
not-
audible.
Sir, you are audible, but it's not there, sir.
Hello,
सर आपकी पीपीटी शेयर नहीं है सर. हेलो
yes, yes, hello, हाँ जी.
सर अपनी पीपीटी आप शेयर करें सर.
अच्छा, पीपीटी शेयर नहीं है क्या?
नहीं नहीं सर शेयर नहीं है.
ओह, प्लीज. So this is share.
Yes sir, शेयर sir. Thank you sir.
Okay,
Continue.
okay. Okay, I start with again. And the electrical measurements of the solid state electronic devices basically. In the first we start to beginning with the resistance. Actually, the first we start with the materials of the solid state materials, and the using of the materials we made the devices basically. So first we discuss about the material characterizations and the material property. The first property of the material is resistance basically, and in our childhood we study about the resistance in the 6th, 7th standard classes. The resistance is the basically this is basically this is obstacles of the charge flow, and this is depend on the conductor length and the area. You are all well known about this phenomena, and this resistance is basically emphasized by the Ohm's law. And the Ohm's law, all or you are the known about the Ohm's law. Basically, when we apply the voltage in a conductor, so what's happened? The charges follow in terms of the electron flow. So there is some obstacles in a charge flow that we can say this is the resistance, and the voltage is directly proportional of the current. So we all are now about this. So when we remove the proportionality constants, the one term R is arise there. So this is the resistance basically, and the resistance we can calculate in terms of the voltage and the current. We are all now about this method and this symbol, and this is the law. Now the Ohm's law basically, the more emphasizedly we can illustrate in this funny diagram and the funny picture. The voltage basically, this is a force. The force is applying on on a charge carrier. But in a charge carrier moment, there is some obstacles. This obstacles is called the resistance, basically. And in a circuits, though the resistance is used in circuits, so in a modern era, the lot of the bar symbols and the different of the colors is on the resistance. You can identify the value of the resistance. You are all order. And now about this phenomena. And in terms of the Ohm's law, when we sketch the values of the data of the voltage and the current, so here, so this is the voltage and the current graph, and the graph slope is showing your resistance value. So this is the graph slope, and the graph slope is indicate about the resistance value, the higher resistance and the lower resistance, basically. So in any current voltage data, so you can calculate the resistance by the sloping of the graph. So one thing, and the next in terms of the resistivity. So this is the part of the resistance, you can say in terms another terms, the resistivity, basically. So the resistivity is basically, this is depend on the length and the area. And how to calculate the resistivity we'll learn about in the next slides. And the resistivity reciprocal of the resistance, you can say the conductance, how the charge is easily flow in a material, so the conductance, basically. And another of the characteristics of the current voltage characteristics, the current voltage characteristics, basically this is calculation used for the calculation of the resistance, conductance and the resistivity. So how to distinguish between the different of the materials, and according to the Ohm's law, according to the resistivity, so there is some highly conducting materials, so they can show the conductors and the non-ohmic conductors, basically, and the insulators. And the non-ohmic conductors, basically, these are the semiconductors which have the resistivity between the conductors and the insulators. And insulators are those materials which have the highly resistives. You can say the resistivity is very, very high. So according to the resistivity, so there is the distinguish between in the materials, the conductor, highly conducting materials of the charge following, and the semiconductors in which the charge following is between the conductors and the insulators. Basically, insulators are those materials which have the resistivities high. And in a real world examples, by using the IV characteristic to measure the conductivity. So conductivity measurements in a different of the semiconductor materials, in the power transmission lines, in the power transmission lines, you measure the current voltage phenomena and then measure the resistance in the battery testing and the solar cell efficiency. So the lot of use of the current voltage measurement. First, when we measure the characteristics of any system, so we apply the voltage, measure the current and calculate the resistance. And basically, this is the current voltage measurement is the behavior of the charge carrier in your system, basically. So now another, how to calculate the resistivity. So the question is how we can calculate. So there is a calculation of the basically the two methods. One is the two probe methods, and another is the four probe method. In a two probe method, basically we apply the battery through we apply the voltage and measure the current. This is the simple. In a two terminal methods, in which terminals we apply the voltage and measure the current, but the four probe method is totally different, because there is the terminals are four terminals, but some difference between the four probe and the two probes. Basically, two probes is not a good method to measure the resistivity of any materials, because there is in which materials you are applying the voltage, and then similarly you measure the current there. So here is the some value of the resistance, which is exactly we are not measure. So we need to the 4-probe method in a semiconductor industry. The 4-probe is used for the measurement of the resistivity. In the 4-probe measurement, basically, there is a two probes, 1, 2, 3, and the 4. And in a 2 terminals, we apply the voltage, and in a 2 terminals, we measure the current. So here is the source is the current. Basically, we apply the current on the outer side of the probes. With the probes is 1 and 4. In a 1 and 4 probes, we apply the current basically here, and we measure the voltage between the two middle probes. So this is the good method for the resistivity measurement of the semiconductor materials and the thin films materials basically. And because there is the resistance value, you can calculate the very accurate. Now the another method is a Hall effect method, and in Hall effect method, this is also the measurement of the materials. Actually, the property of the materials is depend on the two and three parameters. Basically, one is the resistivity, charge carrier concentration, and the mobility basically. So the resistivity you can measure by the 4-probe and the 2-probe method by the current voltage applying. Now the how to calculate the charge carrier concentration and the mobility basically. So one scientist who is developed one method how to calculate the charge carrier concentration and the mobility basically. So the scientist is developed a method so called that this is the Hall effect. In this Hall effect method, suppose if we have a semiconductor piece, so in this semiconductor piece we just follow one current. So constant current we apply, and in perpendicularly we apply a magnetic field in this. So what's happened due to the Lorentz force phenomena? So the charge carrier when move in a magnetic field, so experience a force. So this is the Lorentz force. So what's happened? The which electrons is moving through the constant current, and we apply the magnetic field perpendicularly. So what's happened in this semiconductors? The electrons are or a holes basically. So this is the charge carrier, and the charge carrier experience a force, and they start to move to collect in some directions. And what's happened in this material? So in the opposite directions of and opposite terminals, suppose these terminals is the current terminals, but in a perpendicularly of these terminals, so another voltage is arises. So this arise voltage basically is called the Hall voltage. And so now, so here is also the phenomena of the current voltage. In a Hall effect, we constant current is applied, and perpendicular the current, we apply the magnetic field. And what's happened? The another voltage is arises and develop. This is Hall voltage is called. So there is one factor R resistance is arise, which is depend on the Hall voltage and the current, and is the magnetic field which you apply here. So this is the setup of the Hall effect. These are the permanent magnet. So we put our sample is here, and apply one constant current. So in current, so we apply a magnetic field perpendicularly on your sample. So what's happened, one voltage, this whole voltage is developed in another terminals. So we measure of this whole voltage value, and we know the current value, we know the applied magnetic field value. By the probe we can measure the magnetic field value. So put of the all these values in this formula and calculate the Hall coefficient. And another formulas is in a literature, so we can calculate the mobility, we can calculate the charge carrier concentration in a material. So this is very important method, how to calculate the charge carrier concentration and the charge carrier mobility. And another is the measurement of the semiconductor characteristics is either this is the p type or n type. So because suppose if in any industry, in a device fabrication, we need p-type semiconductor, we need a n-type semiconductor. So how do we distinguish, how to identify, and how to I characterize? So this is the p-type or n-type. So we go to the Hall effect for the measurement of this is the p-type semiconductor, this is the n-type semiconductor, and how much is the charge carrier concentration in this semiconductor. The charge carrier concentration is a Hall concentration or a electron concentration, and the mobility of the charge carrier concentration. So we need the Hall effect. The Hall effect is a very fundamental basic measurement technique in a semiconductor industry, in a semiconductor electronic devices basically. The application of the Hall effect, so basically the big application of the Hall effect in a semiconductor characterization basically. And another application of, you can also you can measure the sensors and etc., and then the magnetic imaging and the thyristors basically. So lot of application, but the main application of the Hall effect is in a semiconductor industries characterization of the semiconductor mobility, semiconductor charge carrier concentration, and the N type and the P type with characterization basically. Okay, and now in a semiconductor industry basically, suppose if we have a some type of the materials which have a regular shape. Suppose if you have an irregular shape material, so how we calculate the charge carrier concentration and the mobility and the resistivity of. So one is the very good method and very precise and accurate method of the resistivity measurement of the charge carrier concentration measurement and the mobility measurement basically. So this is the Van der Pau method. In the Van der Pau method basically we calculate the resistance, we applying the voltage and the current by using of the four terminals. Suppose if we have the four terminals, one terminal, two terminal, three terminal, and the four terminals. So what's happened, what we did in this experiment, normally the exact and recommended method of the probing is this. This is not good, this is also good, but this is not a good. This is a good method, and in this method we apply the voltage here, measure the current here, then we change the terminals, and we calculate the resistance value changing the terminals basically. So how to change the terminals, how to measure the resistance basically? Suppose this is the 1 2 3 4 1 2 3 4 resistance, yani we apply the current in a 1 2 terminals and measure the voltage 3 to 4 terminals. Similarly, we change the values of the current terminals, voltage terminals. So using of this technique, so we measure the resistance R1234. In R1234 resistance means there we are applying the current in a 1-2 terminals and the voltage is measuring in the 3-4 terminals. In a resistance is 3-4-1-2. It means that is we are applying the current in a 3-4 terminal, measuring the voltage in a 1-2 terminals, and the resistance is 2-1-4-3. It means we are applying the current in 2 and 1 terminal, measuring the voltage in 4-3 terminal, and resistance is 4-3-2-1. It means that we are applying the current in the 4 and the 3 terminals, and current is measuring the voltage in the 2 and 1 terminal. So we calculate the resistance in a vertical manner, in a horizontal manner. So there is the 1, 2, 3, 4, 5, 6, 7, 8. 8 resistance value we calculate by using the changing the terminals of the current and the voltage. Now we calculate the resistance value. Basically, this is the resistance R. R is the total resistance. This is the average resistance, and upon the log 2, pi R upon log 2. This is measurement is basically is happening in a thin film semiconductors. So we calculate the RS. RS is a surface resistance, and this surface resistance unit basically we say the ohm per square. So then we multiply of the thickness in RS value, then we calculate the resistivity directly. Now, and this method is also we are applying in a Hall effect. So in a Hall effect, then we calculate the RH value, Hall coefficient in a like this method by changing the terminals. So this is the very accurate method to determine the resistivity, to determine the charge carrier concentration, and the determination of the mobility of the semiconductor thin films. So this is the very useful. Now another method is very fast method. How do we identify the material is a p-type or n-type? So this is the hot probe method, because if you are identifying the material through the Hall effect, either this is the p-type or n-type, it takes some time, because to you repeat the experiment and takes the nearly the half an hour for the you apply the current, you measure the voltage, you apply the magnetic field, you set up the experiment, and then you calculate the value. But here is a very fast technique how do you measure the p-type and the n-type materials. So in this method, what's happened, so we'll take the two probes basically. So here is the two probes. So these are the two probes, and these two probes basically in a one probe we keep this probe as a hot, and another probe we keep as a cold. Just like you can take, normally I did this experiment, and I emphasize to the students by using the multimeter probe. So in a multimeter probe, basically like this is the multimeter probe. In a one probe you first heat, and another probe you keep the cool, and when you guess that this material is get the proper heat, and immediately you touch all these two probes to a semiconductor. So what's happened, so this is the hot probe. So in this hot probe, the majority charge carrier immediately goes to the outside. Why? Because the charge carrier, the majority charge carrier, basically they gain the energy from the hot probe and they move towards the hot probe, towards the outside. So what's happened? They remain only and only the minority charge carrier. And in your probe, there is one EMF is produced due to the Seebeck effect. So the EMF is produced due to the minority charge carrier. Suppose if your semiconductor is a N-type, so there is the EMF is produced due to the minority charge carrier of the hole, and your EMF value is a positive. Similarly, if your semiconductor is a p-type, so there is the EMF is produced due to the minority charge carrier of electron, and the EMF value is a negative. So the EMF sign, positive or negative, so you can see there is the some millivoltage is arise in the millimeter. So in a multimeter, so we can check immediately either this material is a p-type or a n-type by the hot probe method. So this is very interesting method in a semiconductor industry, but not an accurate method. Accurate method is a Hall effect, but you can guess immediately either this is a p-type or an n-type material. Suppose if you don't know the type of the material. Okay, and the capacitance voltage characteristics is also a very interesting and a very important method and very important parameter of the capacitance basically. And in our childhood, basically we know the capacitor. Basically, the capacitor is a two plates, which is the charge storage device. So by the characterization of the capacitance and the voltage measurement, we can measure the basically how much is the charge is stored your device basically. And another method in a semiconductor basically, which use as a capacitance voltage measurement basically, first use how do you calculate the dielectric constant, because the value of the capacitance is C is equal to epsilon 0 K upon D. D is the distance between the plates of the capacitor, and K is the dielectric constant. Suppose if we measure the capacitance value C is equal to epsilon 0 K A upon D. So if we know the area and if we know the distance between the two plates, so we put the value and then we calculate the dielectric constant. By calculation and by the characterization of the capacitance voltage measurement, we can measure the defects in a material. So we emphasize the how to we can measure the defects in a material by using the capacitance voltage measurement basically. So the capacitance is basically measured at the different of frequencies. So this is the voltage and the capacitance measurement at the different of the frequencies. So why we measure the capacitance at different frequencies basically? So in a semiconductor basically, so this technique, so this is very important technique. Suppose if we have a diode, and in a diode basically in a reverse bias condition, we will emphasize in a next slide basically. So in a reverse bias direction, so the capacitor is behave like a capacitor also. So we can measure the defects level in a diode, in a MOSFET, in a MOS structure. So normally the capacitor used as a charge storage device, but in a semiconductor, the capacitance voltage measurement is a technique to determine the defects level in a device. And how to measure? So we will emphasize, we will see in the next slides but we need the characterization at a different frequencies. Why need the different frequencies? I will emphasize it in another slides. So the capacitance measurements so we will emphasize in a device basically. So interface stage measurement, oxide thickness measurement. Okay, we can measure the oxide thickness because the capacitance C is equal to epsilon 0 K upon D. I have already discussed about the formula. And now we discuss about the PN junction basically. So the PN junction basically, one is the P-type semiconductor and another is an N-type semiconductor. What's happened? How to junction is formed? So junction is basically formed. This is a very interesting physical phenomena. When a P-type semiconductor and in N-type semiconductor, when we touch to each other, we make the intimate contact of the P-type and the N-type semiconductor. So what's happened? Basically, P-type semiconductor have the majority of the charge carrier of the whole, and the N-type semiconductor have the majority charge carrier of the electrons. When you touch to each other, what's happened? There is a very interesting physical phenomena is happen because in N-type semiconductor, which have the majority of the electron, and the P-type which have the majority of the hole. So in N side electrons, they are diffused towards the lower concentration of the electron, because in the P side there is a low concentration of the electron, here is the high concentration of the electron, and in a P-type holes, because the holes is high concentration, they also start to diffuse towards the N side. So this is very interesting phenomena because the all side is the majority charge carrier is start to diffuse towards the lower concentration. Like similar, if you have the two beakers, one water level is high and another is a water level is suppose is a low, and you combine to each other by a pipe, so the higher level concentration is diffused towards the lower concentration. So what's happened in this situation? So the when the electrons is moved towards the P side and the hole is diffused towards the N side, so immediately there is a, because a charge sheet is developed on a interface, because the one positive charge sheet is developed on a N side and another is a N negative charge sheet is developed on a P side. And what's happened is the further interdiffusion is stopped when this barrier is arise on an interface. So this is the electric field is arise, and this electric field is stopped further interdiffusion on a two layers basically. So here is basically this is the PN, we can say this is the PN junction, and this PN junction basically used in industry, lot of use, because this is the use as a gate, and first is a rectifier. Yes. So the use of this diode as a forward bias and use as a reverse bias basically. So in a forward bias basically we apply the negative terminals in a sorry, we apply the positive terminal the P and the negative terminal is N. So this is the forward bias basically, and reverse bias is just we apply the polarities opposite. So in a reverse bias condition, what's happened? Your junction is start to deplete towards the terminal sides, and the depletion layer is going to the wide and wide. And in the negative, in a forward bias, basically this is the depletion layer start to narrow. So this is the two basic difference between the forward bias and a reverse bias. Basically, in the depletion layer, in the forward bias is narrowing and the reverse bias is wide. So the use of the current voltage characteristics. So first, in a beginning slides, we told, and suppose for the characteristics of any system, we first apply the voltage and measure the current. And the graph of the current voltage is showing the characteristics of the system. So here is our diode. Our diode characteristics, basically current voltage graph. What is it showing of this? So this is the forward bias graph and this is the reverse bias graph. So what's happened? So this graph, what is showing, what is this graph is emphasizing basically, when we applying the current, there is, when we applying the voltage, there is no current. And in one particular value of the voltage, the current is start to increase. It's similar phenomena is negative. So this is showing the characteristics of your system, your device. So why the current is not increasing up to a fixed value of the voltage? Because your system is just consuming the voltage, not releasing the current. So at this value, your system is consume the voltage, and after this voltage, this start to current. So this phenomena is arising here because in your interface there is a barrier voltage. This barrier voltage is arise during the diffusion of the charge carrier when the interfacing is forming. During the forming condition, this is the manufacturing condition. During the burning condition, you can say when the diode is burning by using the two layers of the p-type and the n-type semiconductors. So at the interface is a one barrier is arise. So this barrier is have the some value. So you can say when we apply the external electric field, suppose the external voltage is less than of this barrier, you cannot find out the current in this structure. So similarly is showing here, the graph is indicating of the situation because this voltage is lower to the interface barrier voltage. When you apply the more voltage comparatively to the voltage is arise on an interface, then it start to current. So you can say this barrier voltage, this is the guard at the interface. So you apply the more voltage, powerful voltage, higher voltage comparatively to this guard voltage, this barrier voltage, then you can get the current. So you can calculate the immediately the by sloping of this graph, then you can calculate the resistance value of your diode. Now by using of this current voltage behavior, you can calculate the by using the diode equation I is equal to I0 e to the power q v upon kt minus 1. Here is very interesting phenomena is you can calculate. So you can calculate the ideality factor, how much your device is ideal. So you can calculate the ideality factor. You can calculate the saturation current. Now on a reverse bias condition, you can calculate the depletion layer value. So this depletion layer value we can calculate. And another interesting phenomena in a reverse bias condition, basically, suppose this is the reverse bias condition, so depletion layer is wider. So in this case, your diode is behave as a capacitor. Then we measure the capacitance of this diode, and then we plot the capacitance value and with respect to the voltage. So there is a one graph, and we can calculate the doping concentration of the semiconductor. So this is a method. Some standard formula is given in the textbook. So you measure the capacitance and the with respect to the voltage, and we plot the 1 upon C. So this is the reciprocal value of the capacitance and the volt with respect to the voltage, and we interpolate the, and then we calculate the slope. There is some standard formula in the textbook, so we can calculate the doping concentration in your diode. Another thing, suppose if your diode, if your system, your this device have the some defects, because the some defects is arise during the manufacturing of the device. How we calculate the defects? So normal people can say that you take the X-ray and all these things. No, because the defects is a very minor level. They are the deep defects, nano level defects. How to measure the defects basically? So we measure the capacitance at the different of the frequencies. We apply the signals of the different of the frequencies. Suppose if you are moving in a street very fast, then we are moving in a street and very fast. What's happened? We don't look and we don't see the major things on your neighbor. Suppose if you are moving very slowly, then you can see and you can investigate all these things is happening in your neighbor during your work. So similar phenomena is in a device characterizations. We apply the lower frequency to the higher frequency. The capacitance measurement. The capacitance measurement basically, these are the capacitance measurement. These are the capacitance measurement of the device at the different frequencies. What's happened? Suppose if our capacitance value, capacitance graph, there is not showing any hysteresis, there is no any difference. But suppose if our graph of the capacitance voltage measurement graph have the some hysteresis, it means there is a defect because the some charge is trapped in the material. Where is the charge is trapped? So obviously the charge is trapped in a defects layer. So by the capacitance voltage measurement, we can calculate, we can identify the defects level. Another device, we have the current voltage measurement of the solar cell and the LED. Basically, the solar cell and the LED is a PN junction. So in a PN junctions, there is the current voltage equation, then we can say the diode equation basically. So what's happened in a solar cell? Solar cell is also similar. This is the PN junction. So in this junction, PN junction basically, so what's happened in case of the solar cell? Photon is impinging on this junction, junction. So there is the photon is absorbed by the material, and there is excitons is arises. Excitons basically these are the pair of the hole and the electron, and they dissociate and move towards the terminal side, and you can get the power. So how to calculate the power? The power is calculate the short circuit current and the open circuit voltage and the fill factor. Basically, fill factor is depend on the squareness of your curve. So here is the diode, and the diode impinging by the light, and the light is absorbed. So this is the diode curve in a dark. When you impinging on the light, the diode start to release some currents. So this is the current voltage graph in a illuminated conditions. How to calculate the power? The power is calculated by the using of this standard formula. Similar phenomena is in a LED. LED is also a PN junction device. This PN junction device, when we apply the external power on this junction is start to emit the photons. So this is the LED. So the LED, how to calculate the wavelength basically? So this is depend on the band gap of the material. So now in the next, so there is a metal semiconductor junction. Up to now we have studied about the PN junction, but another junction is a metal semiconductor junction. So metal semiconductor junction is a very important, very important technology, because you have the daily routine, you are discovering the difference of the semiconductors, and now the material, which material is compatible with your semiconductor, because the semiconductor and the metal. Suppose if you make the device, if you go to the back, if you have this PN junction device. How to use of this PN junction device? You can use when you make the intimate contact of the metal with this semiconductor material, and then take the bonding with the external circuit, and then you can use the material in external circuit basically. So the MS contact, metal semiconductor contact, is a very important technology, very important parameter, very important phenomena in a semiconductor industry. So there is also need to calculate the MS contact. When we make the intimate contact of the metal and the semiconductor, there is phenomena. Suppose if you this is the metal and this is the semiconductor. So when we make the intimate contact between the metal and the semiconductor, so there is the interface. So interface at the metal semiconductor, there is also a barrier. So there is the deep physics is there. So we characterize the MS contact by using the current voltage measurement, and this is the current voltage measurement of the MS contact. So this is the forward bias, and this is the reverse bias behavior of the current voltage measurement of the MS contact. Here is also we can calculate the capacitance voltage of the MS contact, and you can calculate the charge carrier concentration or a doping concentration in a semiconductor basically. So another is is a BJT junction, bipolar junction transistor. So all are you are familiar about the transistors. So this transistor is a 3-terminal device basically, and in this device basically, N NPN and the PNP basically. So this device is used as an amplifier, and the many use in a semiconductor industry, in electronics industry basically. The first use of BJT as a amplifier, and the current voltage measurement of this device is very necessary for the checking of the characteristics of the BJT and how to use as a BJT for the amplification conditions. So this is the input characteristics and the output characteristics. Basically, there is the two circuits. One is the input circuit and this is the output circuit. Actually, suppose if we are using as this structure as an amplifier, so we apply the signal in the input and measure the signal in the output circuit. So this is the input characteristics. We just take the base emitter voltage and take the current and measure the current by using the different of the voltages of and collector base voltage. So this is the collector base voltage, and here is also the output characteristics. In the output characteristics, basically this is the voltage between the collector and the base, and this is the current basically. So in another device, this is because in a VLSI and in a VLSI field, in chip technology basically, you can say the BJT used for the logic circuit, but the BJT is very power consumption devices. Now the researchers use and the MOSFET basically this device is for the CMOS technology purpose, and the metal oxide semiconductor field effect transistors, basically these are the two types of the metal MOSFETs. The MOSFETs is basically the fundamental use as an amplifier, and the another use of the as a NMOS and the PMOS, and this is the combined as a CMOS, and the CMOS is the base and this is the spine of the VLSI technology in the chip technology. So the use of how to the characteristics and where is the your device is basically start to acting. So there's the characteristics voltage is need. So these characteristics voltage behavior is also we measure through the current voltage behavior. So this is the 3-terminal device, and we keep the one is to keep the constant and measure the current. So this is the uh, two types of the in a deflation mode and in a N-channel enhanced mode. So this is the deflation mode characteristics, and this is the N-channel enhancement mode based characteristics of the MOSFETs. So thank you very much for so we now we discuss and we takes the questions in the
Thank you very much, sir, for this brief and wonderful presentation. Atulji, you are here, and RSL Ahmedabad. Kindly make the panelist.
Yes, sir, we are here. And,
Thank you. Thank you.
Photos.
Thank you. Dr. Anuj Kumar, I would like to request you to kindly share me this PPT so that we will share this video as well as this PPT on our website.
Okay, sir.
For all the participants, even after the program. And I'd like to thank all the participants, Dr. Anuj Kumar, Shri Bendikshi Saab, our Director Saab, and all the participants for being with us on this for this program.
Yes, sir, we have taken the photograph.
I'd like to thank once again, all the participants. Thank you very much, sir. Thank you.